Hello everyone and welcome to Control Systems tutorials in Python. In this tutorial, we explain how to define transfer functions and how to compute responses. In this tutorial, we use the Python Control Systems library. By using this library, we explain how to: Number 1. Define a transfer function. Number 2. Simulate and plot the step response of the transfer function. Then, how to simulate and plot the response to arbitrary inputs. Then, how to simulate and plot the initial state response. And finally, how to simulate and plot the impulse response. Here is the copyright notice. This video lesson developed code files and documents should not be copied, redistributed, or posted on public or private websites, public or private code repositories, or social media platforms. This lesson and all the provided study materials are strictly for personal use. Without the permission of the author, this lesson and the provided materials should not be used for commercial purposes and for training of engineers working in companies. This lesson and the provided material should not be used as lecture materials on online learning platforms and in university courses. This lesson and the provided material should not be used to train an AI algorithm or a large language model. Before we start with explanations and with coding, here are several examples in order to illustrate what you will learn in this video tutorial. Over here you can see the second order transfer function with a single pole, and by using the Python Control Systems library, we were able to simulate and plot the step response. Over here you can see the step response. Then, by using the same example and the Python Control Systems library, we were able to compute and plot the response to user-defined input. Over here you can see the user-defined input. Here, we define input to be a summation of a sine and cosine function with different frequencies, and once we apply this input to this transfer function, we will get this response. We can see that the response is nicely filtered. Then, over here on the same example, and by using the Control Systems library, we were able to compute the impulse response, and you can see the impulse response. The impulse response goes to 0, which means that the system is asymptotically stable. Okay, let's start with explanations. In the first lecture in this lecture series, we explained how to install all the necessary programs and software that you need to have in order to successfully follow these lectures. Consequently, you need to have Spider installed on your system as well as Python. Also in that lecture, we explained how to create a Python virtual environment. In this tutorial, we will first create our base work folder, and then we will create a Python virtual environment in that base folder. So let's start. Click here and start command prompt. Over here, navigate to your C drive, and in the C drive, create a new folder and call it Python Control. Then navigate to this new folder, and in this folder create a Python virtual environment. To create a Python virtual environment, we need to execute this command. The name of the virtual environment is environment1. The next step is to activate this Python virtual environment. To do that, you need to type environment1, then scripts, and you need to execute this file. Press enter. And you can see now that the Python virtual environment is active. The next step is to install the necessary libraries. First of all, we need the NumPy library. Then you need to wait for NumPy to be installed. Here you need to be patient. Then we need matplotlib such that we can plot. And finally, we need to install Python control systems library. To install this library, we need to type pip install control. Okay, let's now type pip list to list all the packages. Good. The next step is to start the Spider Python editor and to configure this virtual environment in Spider editor. To do that, we first need to figure out the path to the Python executable inside of our virtual environment. To do that, we need to execute this. Over here, I'm going to execute this simple Python script, and I'm going to print the Python executable path. And here it is. We will need this path. Next, let's start the Spider Python editor. Click here and search for Spider 6 or Spider. You can also use Anaconda to start Spider, as we explained in our first lesson. Over here, we need to configure our virtual environment. To do that, you need to find here option Tools, then you need to click on Preferences, and over here you need to click on Python Interpreter, and you need to find this option. Use the following interpreter, click here, and find the path to your interpreter. In our case, the interpreter is located over here in our folder environment1 scripts python.executable. So let's locate this interpreter. Let's go to our folder environment1 scripts, and here it is. Here's our Python interpreter. Click open, or you can simply copy and paste this path over here. It's up to you. To show you that you can also do that, you can simply copy and paste over here and nothing will change. Click on apply and click OK. Next, you need to click here and you need to click on restart the kernel, and as a consequence you will get this message. Consequently, we also need to execute this command over here. So let's copy this command and let's go back to our command prompt and let's execute this command. This will install Python Spider kernel such that we can use our virtual environment inside of our Spider. So let's wait until this is completed. Here it is. Let's now go back to Spider, and then over here let's close this, and then you'll see that we are connecting to kernel and the error will disappear. Again, you can try this and you can try to restart the kernel and the error will not appear anymore. Good. Before we start with coding, over here we need to set the path to our workspace folder. Consequently, click here and find your workspace folder. Here it is, and click select. Now we are good to go. The first step is to import the necessary libraries. Over here, we are importing matplotlib pyplot as plot, since we need to plot graphs. Then over here, we import the control systems library as CT. Then we import NumPy. Now, to make your life easier, over here I created a function that will plot a graph for given x and y axis vectors. So let's briefly explain this function. This function accepts the following input arguments or the parameters. The x-axis vector, in our case this will be time vector. The y-axis vector, this will be the response of the system. Then we specify the title of the graph. Then we specify x and y axis labels, and we specify the name of the file to save this plot. That is, we will save this plot, and I usually use PNG files. Over here we define the figure, then we plot, then we set the title, x label axis, y label axis, and we adjust the tick parameters, that is, we adjust the font size, we plot the grid, and finally we save the figure and we show the plot. Note over here that I'm using 600 dots per inch to save the figure. My suggestion is to use at least 300. However, I like 600. And this is the function. Next, we explain how to define transfer functions in Python control systems library. To define the transfer function, we first need to consider a general example. In the general case, a transfer function has this form. In the numerator, we have the polynomial of the mth order. We have something like this: am s to the power m plus am minus 1 s to the power m minus 1 plus a1 s, and we have a0 term over here multiplying s to the power 0. S to the power 0 is simply 1. Similarly, in the numerator we have bn s to the power n plus bn minus 1 s to the power n minus 1 plus, then we have 3 dots until the first term b1 multiplying s plus b0 multiplying s to the power 0. To define this transfer function in Python control systems library, we need to define two lists. The first list will group the coefficients of the polynomial in the numerator. That is, the first list is am, then am minus 1, then we group the entries a1 and a0. I like to call this list as num, standing for numerator. Then we need to define the second list, and this list will group the coefficients in the denominator. So we will have bn minus 1 until b1, and the final entry is b0. Once we define these lists, we can define our transfer function. So let's do an example. Let's say that our transfer function looks like this: 2s plus 1 over s squared plus 5s plus 6. Now, the numerator list is 2, 1, and the denominator list is 1, 5, 6. And that's it. Here is our transfer function, and let's implement it. First of all, let's define the numerator list. It is 2, 1, and let's define the denominator list. It is 1, 5, 6. And that's it. Next, to define our transfer function, we need to use the function ct.tf. Notice over here that we imported our control systems library as ct. So let's type w, which will be the name for our transfer function, is equal to ct.tf. And over here we need to specify two lists: the list storing entries in the numerator and the list storing coefficients in the denominator. And that's it. And over here we can simply print w. Or we can also press W in this workspace over here. So let's select this, press F9, and let's see the outcome over here. Here is our transfer function. And we can see that it perfectly matches our desired transfer function. And over here you can simply type W, and you will see this nice print over here: 2s plus 1 s squared plus 5s plus 6. The next step is to simulate and plot the step response. Let's do that. For that purpose, we need to define a time vector. So let's type time vector is numpy.linspace, and over here let's start from 0 and let's end, for example, at 7 seconds, and let's use 200 time steps in between. Now, to simulate the step response, we need to use the function ct.step_response. And over here, we need to pass or to give as the first input our transfer function w, and the second input will be time vector. Here it is. This function will return two things. It will return the time used for simulation, which will actually be equal to the input time, and it will also return the step response of the system. Let's do this. Time returned, comma, system output is equal to ct step response. So let's evaluate this and let's see the output. Here it is. Now, if in this workspace you type time returned, you will see the time, and then you will see also the system output. Here it is. The next step is to generate the plot. To generate the plot, we need to call our function. So let's go back and let's use this function. Let's just do this. Copy. I will paste it over here, and let's specify the things. X-axis vector in our case is time return. So let's substitute it here. Y-axis vector is the system output. So let's put it here. Let's set the title. For example, the title can be step response. String x-axis will be time. String y-axis will be response. And let's specify the file name. Let's call the file as, for example, stepresponse.png. And that's it. Now, let's evaluate this line and let's see the output. If you now click here on plots, you will see the step response. And this is the generated graph. Let's look into this generated graph, where it is. Over here, we need to go to C, Python control, and you can double click here and you will see your PNG file, and you can include this PNG file in your paper or in your student report. Next, we explain how to simulate the response to a specific or user-defined input. To do that, let's define a new time vector. I will call it as time vector 2, and over here, let's use again linspace. Let's start from 0, let's end at 10, and let's use 300 time steps. Good. Let's define our input vector. I will call it as input vector 2. Then let's use sine function. Let's specify the frequency, for example 2, and it's going to be equal to 2 times time vector 2. And let's make the control input to be more interesting, so let's add a cosine function. And over here, let's choose a frequency of 5, and let's again use time vector 2. First of all, let's plot our input vector such that we know what we are actually sending to our system. For that purpose, again, we need to use the plotting function, and we need to adjust the inputs. Over here, x-axis will be time vector 2, y-axis will be input vector 2. Let's call the graph control input. On the x-axis we will have time, on the vertical axis we will have input, and let's store the plot as input control.png. And let's evaluate everything, and let's see our graph. You can simply select and press F9, and over here you'll see the response. So here's our control input. Now if you go back to the folder, you'll see that the file is over here. Perfect. To simulate the response of the system to this input, we need to use the function forced response. So let's write ct.force response, and over here as the first input we need to specify a transfer function. The second one is the time vector. The third one is the input vector, and that's it. This function will again return the time. I will call it time returned 2, and it will also return the system output. So let's call it system output 2, and that's it. So let's select this, press F9 to evaluate it, and over here we will see it. If we type, for example, system output 2, we will see this simulated output. The next step is to plot the system output. Again, I will use the plotting function. Over here I need to specify time returned on the x-axis, system output 2 on the y-axis. Over here, let's call the graph simulated response. Let's leave time on the x-axis. Over here we'll write response, and let's save the file as simulated response. And here it is. Let's evaluate this, and let's see the output. And over here you can see the output. Looks very nice. And let's look at the file. Here it is. Here is the response, and here is the input. Next, let's learn how to simulate the impulse response. Everything is almost the same. First of all, we define the time vector, and to simulate the impulse response, we use the function impulse response, we specify our transfer function, and we specify the time vector. This function will return the simulation time and the output of the system. And finally, we use the plotting function to plot the result. We pass the time, we pass the simulated output, we specify the title, impulse response, set the x and y axis labels, and save the file as impulse response. And let's evaluate this, select this, and press F9, and over here you will see the impulse response. We can observe that the impulse response quickly decays to 0. This means that the system is asymptotically stable. And finally, here's how to simulate the response of the system to non-zero initial state. Again, we need to define the time vector. Then we need to define the initial state. In my case, it's a vector where the first entry is 2 and the second entry is -1. To simulate the initial state response, we need to use this function, initial response. We pass the transfer function, time vector, and initial state. And finally, we call the plotting function. We specify time, response, we set the title, x and y axis labels, and the name of the file that will store our plot. So let's evaluate this and let's see the response. Select this, press F9, and over here you will see the initial state response. Looks beautiful. Okay, that's all for today, and thanks for watching.